All right, okay, good. So, good afternoon, everybody. It's a pleasure to welcome um, um, Fabrizio Nicastro once more here in Crete to give us a seminar. Fabrizio did his undergrad studies in Rome, La Sapienza University. He got his PhD from the same university, although he spent lots of time during his PhD studies at Harvard, CFA, where he stayed for 12 more years. And then he moved back to Rome, and he's now working not at the university, but at the Observatory of Rome Observatory, with occasional excursions, lengthy ones, to Mexico, to Crete occasionally, and lately China, right? Okay.
Yeah.
He's here once more. It's a great pleasure. We are all friends. Oh, meaning we know each other some years, not all. I mean, friends. And he's going to talk to us about one of the topics that he is a world leader, really. He kind of started this work, and he will explain to us why this is important. So it's very, very exciting to listen to the latest results. So Richard, go ahead.
Thank you very much, Sifis. We are also old, by the way, and we are exactly the same age. So,
no way. No way, that's a lie. Hopefully the only one.
Okay, so it's really a pleasure to be here again. Many of you already know what this is really one of my main field of interest. I have been working on these so-called missing baryons thing since 2099, actually, since when the two satellites, first X-ray satellites with high-resolution spectrometers on board, became operative. They are not the best by far, I would say, instrumentation. It's not the best instrumentation to look for these things, as became clear very soon. And that's why this is still a very open field, because with this instrumentation, it has been very, very difficult to actually, very challenging to actually try to detect these baryons. Now, we also know, and that's why I don't write anymore in my titles, missing, because I mean, they are not really missing. We know these baryons are there. They cannot disappear, really. They were there, and actually, okay, then I will probably, this doesn't work. Excellent.
They're okay up there.
What should I do with the okay? Oops. Okay. This was, but I skipped this. If you are you familiar with X-ray spectroscopy and with, well, just a few words then. Why high-resolution X-ray spectroscopy is important? Well, first of all, let me also apologize because the abstract I had sent around and this is why I had these few transparencies before, because I wanted also to talk about another important thing we are doing now with which is kind of related. It's a very complete time-evolving photo-ionization code we are developing, but I will not talk about it. So let me just say a few words of why X-ray, high-resolution X-ray spectroscopy is important. Well, of course, it also allow detection and diagnostic of hot and warm baryons and metals, particularly metals, I should say. And this is done both in absorption and in, and absorption is proportional to the density, electron density of the material you observe, and emission. And emission is proportional to the square of the density, or actually better for metals, to the product between the electron density and the density of the metal. This is important because, of course, the we are talking in most of these cases, at least for the missing baryons, so circumgalactic medium, IgM, and so on, we are talking about very low densities, and the absorption is somehow favored compared to emission because emission is depressed. These are of the order of 10 to the minus 6 particle per cubic centimeter, the electron density, and of course much lower the density of metals. So the emission is very much depressed. And you do this kind of studies for a variety, very large variety of astrophysical objects. Star coronae, of course, emit a lot in the X-ray. The ICM, or the infracluster medium, so clusters of galaxies, the medium which is by far most of the mass of galaxy clusters. And you can do it both in emission, it's done mostly in emission, but also in absorption if you have some bright target behind the cluster. And you can do this wormhole intergalactic medium, which is where we think the so-called missing baryons in the local universe should be. And then you have all sorts of other, of course, it's very important also for AGN and X-ray binaries outflows, but these are densities involved here are much higher, and I won't talk about this at all. I don't know how to move. Click on the slide. Okay, thank you very much. I think I will skip this. You know, this is really basic stuff on X-ray spectroscopy. This is just a gallery, if you want, of what I just said. So these are star coronae, I think. This was an observation with the RGS. I think, yes, I think this is the RGS, the spectrometer of XMM. This is, I don't know, a cluster of galaxies. So this is ICM, a paper by Ciro Pinto. These are absorbers in outflow, AGN outflows, warm absorbers. They have plenty of lines, absorption lines in the soft X-ray band. And this is the galaxy in our own galaxy in absorption in the X-rays. And you can see clearly very hot gas traced by oxygen 7 and oxygen 8, but also much colder gas traced by oxygen 1, 2, and 3. So you have essentially all the colors in X-rays. You can do spectroscopy of all material in all at all temperatures, from very cold to 10 to the 6, 10 to the 7 Kelvin. Okay, now it moves. Okay, so the outline of this talk, I will show you the different phases of the highly ionized baryons in the universe, in the so-called large-scale structure of the universe. These are shock-heated, can be shock-heated, and it's the so-called, the ones that we think are missing, versus the photo-ionized. Photo-ionized are already counted, and I will show you in a minute what I mean by that. I will show you X-ray observation of the Milky Way in particular, and of the hot CGM of external galaxies. This is one of our latest results, and it's very important because it's the first time we do see actually the hot CGM in these external galaxies, And then at the end, very end, I will say a few words on what we can do with fusion instrumentation, X-ray instrumentations, if they become available at some point. So why we do see these photo-ionized baryons? This is a spectrum of a quasar, redshift 3.62, and what you see here is the Lyman alpha emission of the quasar, and then a forest of absorption lines, and this is indeed called Lyman alpha forest. These are hydrogen-1 intervening absorbers in the universe. Now, if you count the column, the equivalent width, and so the column density of hydrogen in each of these lines, you compute the mass of hydrogen, which is distributed in this Lyman alpha filament, and you add up to a total which is the amount of baryons which are predicted to exist in the universe. However, you can do this up to the redshift in the optical, up to a redshift of, say, 2. You cannot, well, you can also do in the optical, you do down to a redshift of 2, and then in the far ultraviolet, you can do the same experiment with a much nearer quasar. This is 3C273 at a redshift of 0.158, and you do exactly the same experiment, and you see the Lyman-Alpha emission of the quasar, but then you have no forest of hydrogen line anymore. And this is, well, this is what triggered the missing baryon thing, because all the baryons in the universe are essentially in the Lyman-Alpha forest are redshift larger than 2, but they are not anymore. They are not in galaxies, as I'll show you in a moment, but not even in these Lyman-Alpha forests are redshift lower than 2. Now, indeed, if you take a census of baryons in the local universe, you have a residual Lyman-Alpha forest. You do, there were a few lines here in absorption. So you have a residual Lyman-Alpha forest even at low redshift, but it counts at most for 20–30% of the baryons. I would say these two actually is probably double counting the same, because this is seen in oxygen 6 and this is seen in H1, but they are probably tracing the same medium. So this is, I would say, between 30 and 40% of baryons are in these photo-ionized IgM. But then very few baryons actually are in galaxy or either in stars or in the cold phase of gas in the disk of galaxies. Some baryons, 4%, are in the ISM of galaxy clusters. As I said before, the ICM is actually contains the vast majority of baryons in a single cluster of galaxies, but clusters of galaxies are rare. And so in the end, when you add up all of them with the counting also the ICM, you make up at most 4% of baryons in the universe. The bottom line is that about 50% of these baryons, we don't know in which form they are. And this is also true for, this is true at large in the universe, but it's also true for galaxies. If you look at single structures, single objects, these are clusters. What you see here is the baryonic mass versus the full mass of these structures. So the circular velocity or the virial mass of the galaxy, of the structures. And when you go, and this straight line is what you would expect given the universal baryon fraction measured as a cosmological parameter through other means. Which is about 0.17 or something like this. So this is the amount of baryons you would expect at different virial masses. And when you go to very large virial masses, clusters of galaxy, the ICM contains all the baryons that should be there. But then when you go to smaller and smaller structure groups of galaxies and then single galaxies, our Milky Way is around here. And our Milky Way is something like 4.3 times the mass of star is the missing mass of the Milky Way. And the problem becomes more and more serious for smaller and smaller structures. So dwarf galaxies have really a strong deficit of mass. So what one thing is that what one thing and what theory tells us is that these baryons get very hot and so difficult to see. This is the distribution in mass, the fractional mass of baryons in the universe according to this particular hydrodynamic simulation. But these results have also started coming out at the end of the 90s, and all hydrodynamic simulations actually agree in temperature. is virtually absent, hydrogen 1, so you cannot see any transition from hydrogen. You have the helium is fully ionized, but definitely all the hydrogen. So you have to go to metals, and the most abundant metals, as we know, is oxygen. And oxygen at this temperature is mostly in its helium-like configuration. And the helium-like transition of oxygen fall in the soft X-ray band. Actually, as a matter of fact, all metal transitions fall in the soft X-ray band, with the exception of iron, which is an abundant astrophysical element, and whose transitions are between 1 keV and 6 keV. But iron is much less abundant than oxygen or carbon. Okay, I skip this and I start going to the result. So when this game started, actually, the most promising object to look at for was the Milky Way, because we see it in the Milky Way. So all lines of sight we observe go through our own Milky Way. So and it goes through everything. It goes through the disk, to the thick disk, to the halo, to an extended halo, CGM, or whatever. The very first thing we published in actually this, well, it's not the very first, but this is a paper in 2003, a Nature paper, in which what we did was to look at the distribution. So just to, I don't have an example, but in the far ultraviolet, oxygen 6 has a transition. The strongest transition is an L transition at 1032 angstrom, and is a doublet, 1032 and 1037. And it's ubiquitously was observed by FUSE, which was a satellite built exactly to do this, to do a survey of oxygen 6 absorbers from our point of view in the galaxy. And what they see, if you look at AGN, you see a redshift 0, consistent with 0, with velocity which are not exactly 0. You see two kind of oxygen 6 absorber, what they call low velocity, and it's an analogous of the H1 low velocity and high velocity absorbers in the galaxy, but this is much hotter medium. Oxygen 6 traced by oxygen 6. So there are low velocity absorber, but there are also high velocity states of this distribution. There are actually two components. They are ubiquitously seen together. You see a line at a low velocity and a line at a slightly higher velocity, and these higher velocity lines cover velocity smaller than 400 kilometers per second. Okay. So what we did was to kinematically try to distinguish among these two absorbers, and this is a plot, a projection in galactic coordinates of the position of this AGN in the sky, and field circles are, I think, negative velocity. I don't remember whether negative or positive, one of the two. Field circles are AGN that have high velocity oxygen 6 with negative velocity, and empty circle with positive velocity, or vice versa. It doesn't really matter. What matters is that they really segregate in the local standard of rest system. Then when you move this velocity from the local standard of rest to the local group standard of rest, they completely randomize. And the opposite thing actually happens to the low velocity absorbers. The low velocity absorbers are completely randomized in the local standard of rest, and then they are segregated in velocity space in the galactic standard of rest, not the local group, but the galactic standard of rest. So for us, these are two very good evidence of the fact that these absorbers are, the low velocity are in the disk, and they are co-rotating with the disk. These ones are, we don't know what they are, but they're definitely not co-rotating with the disk. So probably, most likely, they are not gravitationally too bound to the disk of the galaxy. So probably more extended. So this was one first evidence that made us think these are just the velocity vector components, but they say exactly the same thing. One first evidence that made us think there was an extended component there were in our galaxy which contained lots of hot or warm hot baryon. Oxygen 6 is not really too hot, but it starts to be close to the, it's 2 to 4 times 10 to the 5 Kelvin. Important thing was to would have been to detect the real hot component in the galaxy, and this was the first detection. Actually, this was before we published in 2002 this paper. This was the first Chandra spectrum of the oxygen 7 and actually also oxygen 8 at redshift 0 in our in the galaxy. Exactly, we don't know exactly where because we sit in the galaxy. We only see this line at the redshift consistent with 0, but we don't know whether this and the resolution. Mind that the resolution of fuse is of few kilometers per second was. The resolution of Chandra is about 500 kilometers per second. So there is no way actually to see whether there are more than 2 components, even a low velocity and a high velocity. Most likely there are. We only saw a line, but this was the first evidence of very hot material in the galaxy. Now, of course, this could be the disk and not an extended, these are just some of these. I have a figure here of the oxygen 6 as well. So these are in the same, this is the line of sight through to Parks 2155, the blazar, fuse spectrum of the same blazar. They show the high velocity and the low velocity component in oxygen 6. Okay, so again, as I said, it's you cannot say whether this hot absorber is in the disk or somewhere in a more extended region of the galaxy, a corona, the CGM, we don't know. But what we know is that the disk must be much denser than whatever is more extended. So a corona typical densities are of the order of 10 to the minus 4 to 10 to the minus 5 particles per cubic centimeter, while, or CGM, while the disk is probably closer to 1 particle per cubic centimeter. The ISM average density is of the order of 1 particle, but can be maybe 0.1 or 0.01 particle per cubic centimeter. So what we did was to measure equivalent width and so column densities between of these lines, in particular oxygen 7, oxygen 8, and oxygen 6 in the far ultraviolet, I think. And compare with models which are pure collision ionization models, or which pure collision ionization model, or models which also take into account of photo-ionization from the stars in the galaxy and the external metagalactic field, UV field. Now, of course, this is only important, start to be important at very low density. So what you see here is these dashed lines are these models, hybrid models, collisional plus photo-ionization for densities of the order of 10 to the minus 5, I think. No, it's 4 to 6 times 10 to the minus 6. So very low density. And when you do this, solutions start to be consistent with each other. I mean, these ratios that you see here, which I cannot even read, it's neon 9 over oxygen. Anyway, ratio of lines in the X-rays. The only way to let them actually be consistent with each other is to lower the density of this medium. So again, this was the very first suggestion that there was very tenuous medium somewhere in the galaxy with temperature of the order of 10 to the 6 Kelvin. This was done then again with a much higher signal to noise for this source, Markarian 421. This is a paper by Williams et al. Of 2005. Same game. Actually, well, this is another interesting thing. The oxygen 7 and the low velocity oxygen 6 cannot be together because we measure a Doppler parameter for the oxygen 7 and oxygen 8. Well, actually, this is only oxygen 7 absorber of 40-ish kilometers per second, while at very high significance, the low velocity oxygen 6 has a Doppler parameter of turbulence velocity of the order of 80 to 90 kilometers per second. So these two, oxygen 7 and low velocity oxygen 6, cannot be together. The high velocity oxygen 6 in these particular sources was very faint, so impossible to play this game to see whether the high velocity oxygen 6 was consistent, but at least we could rule out the combination of these two absorbers. With this analysis, we could also measure the column density with small errors, at high precision, the column density of oxygen 7, and this would give us a temperature versus density solution, which lie again in the region of density of 10 to the minus 5-ish, and a temperature of the order of 10 to the minus 6, a bit lower than 10 to the minus 6. So again,
these velocities are Doppler velocities, kinematic,
these are which the velocity I was talking about before. So the velocity with oxygen 6, those were Doppler shifted. The one I showed at the beginning, those are kinematic velocity, okay? These I'm talking here are Doppler parameters, so width of the line. But the width of the lines are not resolved. They are resolved here for oxygen 6 in the infuse, but they are not resolved in oxygen 7. So in oxygen 7, all you can do is play with the curve of growth of these three transitions that we see, all of the three of them in this source, K alpha, K beta, and K gamma, and you get this intersection, which is the solution. And so you can disentangle Doppler parameter, meaning width of the line, and column density, which are otherwise degenerate because lines are saturated.
So you attribute that to kinematics within the cloud itself. It's not that the whole cloud goes away with 60 kilometers.
It's probably, well, okay. So this is actually interesting because this is quite a low velocity. Interestingly, also the dynamic of kinematic of galaxies in the local group as this, it's very low and has this kind of sigma velocity, turbulence velocity, dispersion velocity, sorry. And actually this was our original suggestion. We thought that this gas was actually local group gas. Now I'm not convinced anymore. I think it's more kind of CGM. But again, our local group is the distance between us and M31 is 1 megaparsec. The radius of the local group is of the same order. The CGM, the virial radius of our galaxy is 250. The virial radius of M31 is of the same order, 300 kiloparsecs. So when you put things together, it's difficult to really distinguish between CGM of these two big galaxies and medium in the local group. There is probably a bit of everything. But anyway, okay. So yes, those are turbulence velocity of the gas. Okay, those were two sources. Then 20 years almost passed, and so it was about time. The archives were full of because I don't know if you realize that from the spectrum, but the very difficult part is to have lots of photons in the continuum. These are very small instruments. RGS and ADTG, channel ETG, and XMM-RGS have effective area between 10 centimeters and 40 centimeters. So they are very small objects. Getting lots of count from distant AGN per resolution element in this high resolution spectra is very, very difficult. So see the contrast of these lines, detect these are kind of absorption lines, is extremely challenging. So to populate the archive of bright AGN with good high resolution spectra took almost 20 years. But now the archives, especially the RGS archives, because XMM observe with all instruments at once, while Chandra, you have to ask for the high resolution spectrometer if you want. So, but the XMM archive is really full of bright enough AGN and bright enough X-ray binary. So the game we played, this was in 2016 with a PhD of mine. The paper was never published. And this is why we are publishing now, but in a more with a more extended sample. But this was our first sample in 2016. What you see in black is AGN, high galactic latitude sources, and in red, the binaries, X-ray binaries of our sample. The hope is to find the difference between the amount of absorption of the X-ray binaries that only sample the disk, so it can only be in the disk, and the amount of absorption, if there was an excess of absorption toward AGN. If you look at equivalent width, you don't see any difference. Here again, red and blue are AGN are blue and binaries are red. You don't see any difference in the equivalent width of oxygen 7, but mind the equivalent width of this amount, 10 above, I would say above 5 milliangstroms for oxygen 7 are heavily saturated. So what really matters is not the equivalent width, but the column density. Well, here I show you how saturated they are. AGN are almost fully saturated, and X-ray binary is a bit less. These are the two limits, unsaturation and full saturation. So you have to try to disentangle. To derive the column density, you have to try to remove the degeneracy between Doppler parameter and column density, and to do that, you need at least two transitions. So we selected only the oxygen 7 absorbers that had both K alpha and K beta for both classes of objects, and you see that there is some difference between now between the column density. Now this histogram is column density, not equivalent width, between the column density of binaries, oxygen 7 column density of binaries, and the ones that you see against AGN, with the AGN being thicker than the binary. So again, this suggests that there is something beyond the disk of the galaxy. This is just to show that there are at least two phases in temperature. There is a cooler phase and a hotter phase. Temperature are between 10 to the 5.7 and 10 to the 6.2. By the way, 10 to the 6.2 is also the virial temperature of the Milky Way. So you would expect actually lots of gas to be in the halo of the galaxy at this temperature, as you do see in clusters of galaxies, in which the ICM is much hotter, but just because the mass, the virial mass is much bigger. Okay, then in 2000, very recently, we repeated this game with a more extended sample. Now, of course, just to make things simple, red is AGN and blue is binary, so exactly the opposite. This is a work made mostly by this woman, this PhD student at the University of Xiamen. She will be looking for a job in about 6 months. And this paper has been recently submitted to Science. We'll see how it goes. So these are the two samples. And what we do now is to try to be a bit more quantitative. So we feed a cylindrical model, exponential model, disk model, to the binary, the blue sample. This is now versus distance, because for binaries we know distances, and extended to latitude, galactic latitude for the AGN, which are in red. You feed the binary with a disk model, density model. This is for oxygen 7 and this is for oxygen 8. And then you extend this feed to the high latitude sources, and you see there is an excess of column density. This is column density times sine of the galactic latitude. There is an excess of absorption in for the extragalactic sources, meaning again that there is something beyond the disk of the galaxy. And then if you add to this component another density component that feeds the CGM. We try to model, this is the Muller-Bullock profile is much flatter than a typical beta model, which I personally prefer. But the beta model are typically used to fit profile, gas profile, density profile in clusters of galaxy. But anyway, both models can, of course, kind of fit or reproduce this excess. And when you compute the mass of this excess for the model, so this would be the missing mass in our own Milky Way, the mass that is missing. And this is the mass in this component, this extended component, up to the virial radius. Actually, the virial radius is here, 250 kiloparsec. The flat profile reproduces better, perhaps, the missing mass, but both feet tells you that a large fraction of the baryon mass in the galaxy is in this extended CGM component. How long have I been talking? Too long, probably. So let me just go very quickly. Now, this is all I said so far is our own galaxy. And this is easier to do because any line of sight we observe goes through the galaxy. To detect, but of course, if our own galaxy has a hot CGM, all galaxies, at least like ours, should have a hot, so L-star galaxies should have this hot CGM. But looking for a hot CGM in galaxies with instrumentation that can actually detect emission from this very tenuous material would be fantastic, but we don't have this instrumentation. The only hope is to have a source which is bright enough beyond a galaxy or at some impact parameter from the center of the galaxy and hope to look for the CGM there. Of course, you cannot do this blindly. You need some tracer. And so, for example, this has been done a lot by this COS is the spectrometer, far ultraviolet spectrometer in the Hubble, the HST. There have been several surveys of COS-HALO surveys to look for exactly the way I say, to look for bright AGN in the background of galaxies. So they had a field of known galaxies with no redshifts, and then they picked a few quasars in this in the background of this in this field, and then they measured absorption in oxygen 6 and associated to each oxygen 6 absorber or Lyman alpha or magnesium 2 absorber. Actually, these are cooler, is cooler material. They associated to each absorber a candidate galaxy association with an impact parameter, of course. And this impact parameter go between 50 and 300 kiloparsec typically. What we did was to take two of these big surveys and see whether there were in the RGS archive spectra of the same laser to do the same work with in X-rays and see whether we could detect the hot counterpart of these Lyman limit system, they call it, these cool clouds of gas. And the idea again is that these cool clouds are embedded in this hot medium, perhaps pressure confined, perhaps falling in from the outside. No one knows, but this is what people think. So we had now the redshift of the galaxy of the absorber as a signpost, and if we find X-ray observations of these quasars, we can try to look for oxygen 7 at the same redshift. Now, out of something like 40 quasars, we only found 3 quasars in the RGS archive with sufficient signal to noise in the RGS spectra to look for these features. Now, when I say sufficient, it's really barely sufficient. We observed these spectra one by one, and we could detect oxygen 7 at significance of 1 to 2 sigma. But then we stacked these things together. And now the important thing I want to point out here is that all the galaxies associations are L-star kind of galaxies. The average mass of the halo of these galaxies is of the order of that of the Milky Way. The virial radius is 200 kiloparsec like the Milky Way. So these are three L-star galaxies. These are the average properties of the galaxies. The redshift, the average redshift is 0.276, and this is what we found. Oxygen 7, K alpha and K beta absorber detected at a combined significance in the stacked spectrum of 6.8 sigma. So this was published last year in the APJ and is the first published detection of hot gas intervening at the redshift of 3 Lyman limit systems in external L-star galaxies. We played the usual game. We derived the column density of this, the average column density of this absorber that you see here. We derived the by doing an assumption on the metallicity, but this is an assumption actually assuming that this is the same average metallicity that they see in the Lyman limit system. So assuming that the two components, the two phases have the same metallicity, we derive the hydrogen equivalent column densities. These are, I'm not going to explain you why you have these two versions of the, but essentially you see the two contours sample the same column density and temperature. Again, very much consistent with the virial temperature of these kind of galaxies with mass of 10 to the 12 solar masses. And when you extrapolate this, try to fit with a beta model with these beta indexes, which are essentially for isothermal gas, S should be expected, you can recover almost, I would say, definitely all the mass that is missing in these three particular galaxies. So one is full recovery of the missing mass, but at least I would say 70%. I just want to close with this transparency that shows you the same plot I showed you, one of the plots I showed you at the beginning that showed clusters of galaxies versus dwarf galaxies. So here now you have the halo mass, the dynamical mass from 10 to the 12 Milky Way-like galaxies, all the way out to 10 to the 6, which is very massive clusters of galaxies. And again, this is the baryon fraction, universal baryon fraction. And these are the same points I showed you before, and the black points are instead from Rosita. Rosita was supposed to try to do this, to detect these baryons in groups. Unfortunately, you see there is a strong bias due to the sensitivity of the mission. So this band here is due to the fact that you are not able to see these gas anymore with Rosita, with the Rosita survey. But interestingly, if you put the points which are derived with the way I said for our own Milky Way and for the so Zoo Nicastro's 23 is for the three external galaxies. Zoo is the Milky Way. Bregman is external galaxy done in a completely different way through Sunaya-Zadovich measurements. They all agree essentially for Milky Way-like galaxy to be kind of consistent or much better consistent with the baryon fraction of the universe. That is all I have. Just let me touch upon the future. So what you see here is what we have now, Chandra XMM Newton, and normalized to Chandra. This is a figure of merit for detectability of these lines. It's essentially the product between the resolution, the resolving power, and the effective area under square root. And XMM is slightly better than Chandra because the area is 4 times larger. Then you have CRISP, which is of the order of Chandra. Well, CRISP would have been of the order of Chandra because it's blind where it needs. It's now blind, but it would have been almost of the same order of the LTG because the resolution is worse than the RGS actually also the area, the effective area is quite larger than Chandra. The real breakthrough will come with Athena. This is a factor more than an order of magnitude better than the Chandra ETG. But we can do also fantastic things with these two missions, which are, this is a Chinese planned mission, CAPS, and this is LEM, which is one of the American US probe just submitted about a year ago, of which we will know soon. The two missions are very similar, very large grasp mission to detect emission actually from these structures, from this gas. And then these are grating missions. So these are calorimeters. These are gratings, Arcus and Lynx. They will be way better. Arcus is actually, well, way better. This is of the order of Athena, but way better than Chandra for sure. Arcus is another probe in this US round. And Lynx is something that probably will never happen. I don't know. Since I work for Athena, it is my duty to show also, and in particular for the SIFU instrument, it is my duty, and it's a pleasure to show these, what we will be able to detect with Athena within a total of 4 megasecond against, if I remember correctly, yeah, 26 lines of sight with AGN, about 50 system in absorption between, it really depends on the resolution. This is 3V and this is 4EV, but I would say between 40 and 50 system in oxygen 7 and oxygen 8 in at least 2 lines with Athena. This will double if you consider lines of sight against also bright GRBs. And this is the kind of spectrum that the SIFU spectrum that you will get from one of these systems, in particular along these lines of sight. This is a simulations of an hydrodynamical extracted from a line of sight extracted from an hydrodynamical simulation. I think it was General Striker, yes. And you see detected clearly, I think, 5 of these systems in many more than one line. And I stop here. Thank you.
Thank you very much. So questions here, first? Yeah.
It's just a general question, Fabrizio. What is the warm phase? Is it sort of like these are not clouds, right? This is sort of like the idea is that it's
you would expect it to be homogeneously. You would expect it.
Clusters.
Yes, you would expect. Yes.
Do you expect to have structure?
I'm sure it would not be a very homogeneous thing, but it shouldn't be too structured as well.
So to go back, when you make this measurement.
Although, let me add that there are evidence also for supervirial temperature. There is in some of these objects, you see neon 10. Neon 10 is not compatible with this temperature. It's quite higher temperature. So if it is still, but I suspect that this neon 10 may come. It's only a few lines of sight, actually 2. One of which we know crosses a supernova loop remnant, radio remnant. So there may be very hot gas there in the disk, and this is why we are seeing a neon 9. So neon 10. So I'm not sure this is actually a second phase of the CGM, which would mean structure because you have 2 temperature phase, or perhaps it's just.
And since you have a few lines of sight from our own galaxy, by the column densities that you measure, can you comment on whether it would be sort of like, because you would be in a spherical distribution around the galaxy or not, or is it uncertain to say?
You cannot, we tried that, but you cannot say whether there are, for example, in different directions, whether you will
Yes,
see.
because you go through it.
Yeah,
if you
yeah,
go towards
but-
above the anti-center.
Right, exactly. We tried that, but you know, the anti-center versus the center is only 10 kiloparsec our distance from the sun compared to the, or 20, compared to the 300 kiloparsec, which you expect for the virial radius. So you are not sensitive to it.
So the assumption is that you have this halo around its galaxy, which is a few hundred kiloparsecs in size,
Yes.
And the mass, the estimates that you see.
And the temperature most likely, if it is virialized, the virial temperature of the galaxy.
Sorry for why did we realize since it's shape high?
Oh, well, it is virialized with the mass of the galaxy, like the ICM is. ICM is not fully virialized. There are cases in which it's not virialized at all because of probably feedback, but most clusters of galaxies are virialized. So it all depends whether they had enough time to virialize and also whether they are not disturbed by something. Galaxies have an AGN inside, so they may do some mess to this. For sure, yes. So yeah, but you're right. It's not it's a naive expectation here.
It's a zero
Yes.
explanation. If I can get
So then you can probe the dark matter if it's realized through this. You know that
I'm thinking, but I don't know if you know a way of doing it.
no, you know there are claims of galaxies that are empty of dark matter, like dwarfs that were detected there. So, but this, if it is realized, it's a probe of the total gravitational potential.
Right, the dynamical mass, so it's mostly dark matter, of course.
So then it's a probe of dark matter, right? So you can use these as an independent probe of dark matter.
Very independent though, because you have to assume that you are looking at the virialized, the date is 10 to the 6 because it's the virialized temperature, and so the mass is 10 to the 12, and so it's mostly dark matter. It's very independent, but yeah, once we'll be able to really look at this matter in the near by galaxies in emission, so you also actually possibly now resolving is kind of tricky unless they are very, very nearby, because the spatial resolution of even hubs and LEM, they are not very high. But anyway, once perhaps with enough data, good quality data, you may try to say something. By the way, I don't know if you, there are a couple of papers by a group of in Rome, Silos Labini, and collaborators, they claim that actually they've redone the analysis of all distances of stars with Gaia, and they claim that our the rotation curve of our own galaxy is much more consistent with no dark matter than before claimed. But yes, this is just out of curiosity. They still need some, but they say it's not extended. It's much more localized. No, flat actually in the disk. Whatever.
So Fabrizio, to follow up on the spatial distribution of the sources and the coordinates, do you see any correlation or any anti-correlation of the paths? Like when you look in the direction of the
A paper we published in 2016 was about this. We claimed that the best fit you could get in terms of density profile for these extragalactic lines was by introducing a parameter which was the radius of this, an empty region in the center, and with a radius which was a free parameter, and it would get to 6 kiloparsec, which is the radius of the Fermi bubble. Yes, but it's again perhaps a bit too over modeling the data. Honestly, I have to say. But if you let it fit, they would go to these sites. Yes.
Next question. Yes. Thanks, Fabrizio.
Thank you very much.